Harmonic is a component whose frequency is a multiple of the fundamental, right? The multiple is an integer value, 2, 3, 4, 5, 6, up to infinite. In symmetrical AC waveforms, we have a spelling error, the even harmonics are 0. Average value is 0, right? And the reason is, when you call symmetrical, what does symmetrical? Means that the positive part is equal to the negative part. And if you do a fast Fourier transform, right? And that's how you do it. You get a distorted waveform, and you do fast Fourier. Fast Fourier is going to give you the 60 Hz plus any harmonic. You are not going to see any even harmonics. They are 0. And so all what you have is per 5, 7, 9, 11, 13, 15. Only the odd numbers. In ungrounded systems, triple harmonics are 0. So if you don't have a ground, you're not going to have any multiple of 3. The 15 is gone, the 9 is gone, and the 30 is gone. Think of an induction motor. What is an induction motor? A three-phase load. It's connected in Y. The Y normally is inside the motor, but it's not grounded. The frame is grounded, but not the start point of the motor. So I wouldn't expect to see, if I'm using a drive, an inverter to control the speed of the motor, like the ones that ABB Baldor produces, I wouldn't expect to see a third harmonic. I wouldn't expect to see a ninth. So in three-phase systems, you only expect to see the 5th, the 7th, the 11th, the 13th, 17, 19, and so forth. If you see a second harmonic, it's in a single-phase system. If you see a third harmonic, tells you that there is a single-phase load. So why I'm saying this here, this probably needs to go to the next chapter, chapter 8, that since I've been talking. Because when you place capacitors, I thought I had it, but anyway, what is the impedance of a capacitor? 1 divided by omega c. Let's assume that the capacitance stays constant. It's not a function of frequency. So what's going to happen as you increase the current going through the capacitor? So here it is, right? So what's going to happen as those harmonic frequencies increases? You see the impedance, what's happening? Decreasing. So those capacitors are going to be sync. In ungrounded system, triple harmonics are 0. So that's the reason why when we talk about here, right, if you look at the red and this cone, right, ground will act as a sink for triple harmonic. So if you have a ground connection on that Y-connected capacitor, any triple harmonic that is being put by your system will come through here and it will come here. So what's happened with the triple harmonics? Or any current that goes through the capacitor. What's happened with any current that goes through any piece of equipment? What do they produce? Heat. Correct. Losses, right? Power losses. Any current produces losses. Whether it is your smart iPhone, whether it is your electric motor, electric car, current produces heat. I square R. And if it's three-phase, you multiply by 3. So, and what's happened with heat inside a capacitor? A capacitor has an electrolyte between the two plates. And what's happened with heat? It will basically evaporate the electrolyte until you got a disaster, right? So, that's the reason why here I have the delta next to that. Because if you have a delta connection, right, the capacitors, they won't be subject to triple harmonics. So this is the problem that you have when, right here, right, this capacitor, how is this capacitor connected? If I show you that circuit, how is that capacitor connected? Well, it's in parallel with the load, right? The load has a resistance, right? And a reactance, right? Right? So the capacitor is there, and that's the load, and there is some resistance in that. But either I can use R and X, right? Or oops. Or just use the current and the voltage. But if you have this, and this is a three-phase system, what is the assumption for this capacitor bank? How is the capacitor bank connected by using it like that? How can you connect any piece of equipment, three-phase piece of equipment, can be connected in Y or delta, right? So if I'm having that circuit, what is the assumption that I'm having? That capacitor bank, that value of C that I may have used somewhere is what? Is a Y connected, right? Obviously, in this analysis, there is no third harmonic, right? Because everything is fundamental frequency. Now, if I do have a capacitor that was given to me, which is connected in delta here instead of Y, right? What do I need to do? A delta Y transformation, right? So what do? You get XC and you divide by 3. So sometimes the capacitor bank is not grounded to avoid that third harmonics, right, flow through that. The problem is that when you do that, this point here can be flowed, right? And if you have a fault, right, across one capacitor, right, then the neutral can become the line voltage, right? So you have to be careful about that. So the reason why you would like to ground it is because you want to avoid currents going through here, right? Sorry, because you want to define the voltage at this point to be 0. But then you have triple harmonics. If you suspect, and what I'm saying is, because if you go and work, right, for an electric company, you need to tell them. You know, if they come and they say, well, are we going to ground this capacitor? And they say, yes. Well, do you have harmonics in the system? Do you have triple harmonics, right? And then if you have triple harmonics, do you suspect? Ask the proper question. Do you think that there will be a problem? If there are a problem, what you do is you design this as part of a harmonic filter. And this is just for general knowledge. You're not going to have any question in a test, and you're not going to have any question in the homework, right? Because it's not there. But that's for your knowledge. So don't think that placing of capacitor is as trivial as the example is shown, right? The initial calculations are like that. The only thing is that how do you design a harmonic filter? You calculate the capacitor as you need for power factor correction. But then you have to add an inductor and a resistor. And then it becomes, when you have an inductor and a capacitor, what do you have? An oscillator, right? Remember, 1 over the square root of LC. And so there are some equations there that, if you ever work in this field, probably you're going to come in.